Hey guys, so in one of my last videos not too long ago while we're doing this exhaust series, I wanted to finish on the collector flow tests. So I went to Lowe's and we now have a 1.5 inch and a 2 inch, and as before they have a nice tapered edge so we don't have any sharp edge flow results. So we're gonna go ahead and flow those then. So we flowed these. All right, now this one we're not going to flow today, and the reason for it is my flow bench is a 4-inch bore, and it's nice smooth taper, okay? So we're just going to flow the bench. Anyway, so after that, what we're going to do is then we're going to put these, each one of these, on a pipe, okay? And now push that all the way. I will push that all the way down, but then if I don't drop it, what we're gonna do is we're gonna flow it with a pipe, okay? Now I'll push those all the way up so that it's not a sharp edge there, but I want to be able to get them out pretty easily without having to lube them up. So that's what we're gonna do. All right. So we'll flow test each one of them. All right, and those will go on there just like that, okay? And I'll clamp that down and get it all good to go. But anyway, so I'm gonna flow all these collectors, and then I'm gonna put a pipe on them and stick the pipe down in there. We're gonna flow it, okay? And then the last one, I'll just flow the bench by itself. And the only thing I don't like about flowing the bench by itself is something we talked about in one of our building a flow bench videos, is when you have airspeed going past your suction line going to your manometer, Bernoulli's principle, we'll not get into that too much, but the airspeed going past that can change slightly your reading on the manometer. So what I'm going to do is I'll flow it, and then I'll block part of that off in just such a way that it'll try to deflect the air from going fast past that line. But regardless, I'm going to do the flow tests, and then I will show you the results. Okay, so I just finished the flow test. Here's your results without the pipe and with the pipe. The 4-inch doesn't have a pipe because I flowed the bench, and if you look at the bench, it steps from a 4-inch all the way up here, and it steps up to a 6-inch. So we're simulating it with a pipe. So, and it's a nice smooth taper as well. It's hard to tell with how dirty it is, but it is a nice smooth taper. So this is what we're looking at. What you'll notice is the huge drop in the 1.5 inch and the 2-inch. But as you get larger and larger, you start seeing less and less drop in flow. The reason for this is with 1 psi test pressure, which is 28 inches of water, you have airspeed that is really getting up there. And when airspeed gets up, you have turbulent flow. Something called Reynolds number, and I'm actually going to do a video, my last video I believe I'm going to do on this exhaust series that I've been doing. I'm going to talk about Reynolds number a little bit and how we differentiate between turbulent and non-turbulent flow. But this is turbulent flow, and when you get turbulent like this, you have these little eddies that form. So when flow gets, you have these little eddies that form, and they're just like little vortexes. And when you're going through the pipe, these eddies generate, and as you get closer to the wall, you have a nice laminar flow layer right next to the wall. But right as you get to the transition layer, which is a little bit higher now, granted this is not to scale, but you get a little laminar layer, and then you have a transition layer, and then you're going to get into the turbulent air, which is going to have lots of eddies in it. And those that's going to cause you to reduce flow, your flow rate. You're going to have back pressure in the pipe. And again, that next video I'm going to talk about Reynolds number, turbulent flow, how we determine if we have these eddies forming, and that kind of thing. So you're having that happen in the 1.5 and 2 inch, but as you notice, and these are significant flow drops, especially the 2 inch. And again, that's just these little eddies forming, and that's what happens. So that's why I wanted you to see this. 2 3/4 and 3 inch, they're pretty close together, so their flows aren't going to be astronomically different. But as you can tell, there's a lot less flow drop when you start getting to larger pipe at the same test pressure. This is critical. At the same test pressure, as the pipe gets larger, the airspeed slows down, and you have less turbulent flow, less eddies forming, less of these little guys that form, okay? And when you have less eddies form, you have more flow. So this is why when you're doing these collectors, especially on these little guys here, they're getting down below this 2.5 inch and 2 inch. A lot of those shorties are around a 2 inch. You get a lot of turbulence in that exhaust, and that exhaust is not at 1 psi, it's significantly higher. So you have a significant amount of back pressure that builds up in the exhaust. So back pressure is a myth. I don't care where you hear it or who you hear it from. We want to reduce back pressure at as much as humanly possible. And now I'll talk about back pressure on the next video. It goes into Reynolds number, how do we calculate Reynolds number, and we'll get into Darcy-Weisbach and some of the other Colebrook equations that we use to get to how much back pressure we have in a pipe with such a violent system going on. It's a little complex, and I'll try to make it as simple as possible so that we can kind of go through it and see how we determine back pressure and what effect does that have on wave tuning and all those other things. So, all right. So the last thing I want to do is I want to do a flow test doing a step collector. So this is a 3 inch with a nice smooth transition going down to a 2 inch with a nice smooth transition. Okay. I'll do a leak check. I'll put a cover on this. I'll leak check it around this little piece here, and then we'll flow it, see what it flows, see what kind of interested. We'll see what it does. Okay, so just finished flowing the step collector here. All right, and I just showed you a little clip of flowing it 28 inches of water. So 485 CFM, which is just marginally better than 2 inch by itself, and this makes sense. The 2 inch by itself has got a little bit of a sharp edge here before the transition, and having a nice smooth transition here, going straight into a very smooth transition there. I can see that adding 10 CFM. But again, I wasn't expecting it to flow any more, or maybe just a little more due to that transition, and it flowed 10 CFM more than the 2 inch by itself. This is a pretty popular little modification people do in their after their header collector. If their header collector is a 4-inch and they want to put 3-inch pipe out the back, because it's easier to bend. I don't know, that's just something people do. There you go. A little bit better flow here. Now granted, this is just testing at 1 pounds per square inch, and we're not in a violent atmosphere of an exhaust system, but velocities will be much higher, pressures will be much higher, flow will be much higher, but just a representation at 1 PSI of just air, not air fuel, carbon mixture. There you go, 485 CFM. Hopefully you learned something from this video and you can apply it to your own applications. I'm going to do another video as soon as I can. If I can film it in the next day or two, I will. But I'm going to be going over several things. There's some old formulas out there that I'm going to go over that are just old school formulas that we use to choose our exhaust system setup. And then I'm going to go over a little bit more detailed and some science behind it, and how I determined what I was going to use for Old Red and why I chose what I chose. Alright, that's it for this video. See y'all.